Hello. Very good afternoon to everyone. I hope you can all hear me, and if you do, please put it in the chat so we can start off with the workshop. Okay, yeah, thank you. All right, great. Let's get started then. First of all, apologies for the postponement of the workshop yesterday. Me and Chakita had some scheduled meeting, so we had to kind of skip this one and push this one. But I was able to make time today, and I would like to finish this second part of the workshop, which is actually going to be really exciting because this part is where we actually build a neural network, and it's a basic general roadmap for you to start building any deep learning model with PyTorch. There are some fundamental things I'm going to go through which you have to know. So another thing before all of this is that this workshop is intended to give you a first starting step. I can't promise that I will be able to go through everything and be as clear as you would like me to be, but this is something that's to urge you to go forward, take the first step, and look forward to other resources, do small projects, and keep learning. Sort of, this is sort of like initiation. All right, let me start the recording and we shall begin. Okay. So again, good evening, everyone. Thanks for joining me here on this workshop, a gentle introduction to PyTorch, the session 2. I hope you were present during the session 1 as we covered some basics and important concepts of PyTorch, such as tensors and so on. But either ways, I'll be having a small review of that. And today's speakers for the session are myself, Prajwal, and I'll be going through the theory and concepts and the code required. So today's agenda is first thing neural networks. I hope that you have gone through the playlist that I have sent you in the mail. It's a really good playlist by Grant, and this channel 3 1 Brown is something that's really good, and it has a very intuitive explanation of neural networks. So the first thing we're going to do is neural networks. What is neural networks and what exactly do they do? Second thing is activation functions. Now this is sub part of neural networks, but I think it's something that you should not have doubt in. Third thing, in classes in Python, a small review. The reason being that when we are developing neural network models or models for anything, if you want to build GANs or RNNs, you would definitely need to know classes, right? I mean, you probably do know classes, but there are small subtle points which I would like to go through. The fourth point is data loaders. Now, data loaders are a very strong utility tool provided to us by PyTorch, and it's really excellent. And let's learn to harness its powers for our this one. And the last thing is building a model with the Mnist dataset. So we're going to go with the classic example of the Mnist dataset. Those who have worked with TensorFlow might actually know it because it's like the first introduction to the world of machine learning or deep learning. They bring it forward around 0 to 9 digits, and you classify it. And those of you who have gone through the videos, that's Grant Thompson's other playlist, 3 Blue 1 Brown. It is there. Just a minute, I'll take a second to address a query here. Sankalp, yeah, it has been recorded. In the sense, since this is a YouTube live, I'm pretty sure that it will be there after this. All right, getting back to this. So let's start off with the first thing: neural networks and introduction. So I hope you have gone through the videos on neural networks. Like I keep repeating because that's the most intuitive explanation of neural networks I have ever come through. It's really brilliant. So neural networks are modeled loosely on the human brain. That you should know by now. They were inspired by how how the neurons connect and how the neurons fire and everything. And they brought it to a mathematical model, right? Now let's just go through something I'd like to show you before the next slide is this. All right, for those of you who don't know, TensorFlow offers a neural network playground where you can just experiment with a bunch of neural networks, right? So you don't need to write code or anything. There's just a bunch of stuff here, and all you have to do is just click on the run button to run it. Just move a few things here and there. So just to tell you what a neural network is, I'm going to be using this example just to show you how they work. Before that, let's just go through a review of what we have learned before. The first thing we thought in the last session was tensors, and I hope you remember these basic fundamental functions, right? Toss the tensor from numpy, once like, and so on. Second thing is attributes of a tensor, that is shape, dtype, and device, right? Next thing is operations on a tensor. Matrix multiplication is the most common operation, and they can be performed via two methods using the at symbol or mat multiplication function. And the rest of the arithmetic is pretty straightforward, plus minus. Just be careful of the shapes. And like we have gone through in the last class, there are in-place operations. So what in-place operation does is, now what you should know one thing, that as programmers we always try to make sure that we don't waste resources. Usually when we use t1.add without the underscore, it ends up creating a copy of t1 and adds that to 2, right? It does not add it to t1 itself. In essentially we're creating a new copy. So as programmers, we are very conscious of our space availability. So this in place operations are something we use to handle that, right? In this case, a copy is not created. So 2 will add it directly to t1 in its direct memory space. Next thing is the most important part, t1.item. So if you have a single element tensor and you try to print it in Python, you really won't find much to do. But if you use item, you can convert that particular thing into a Python item and you can print it. This is a review of the tensors. Let's go to the next thing, the back propagation. This is simple review. It's a small model. You get an input, you get the output, you compare the input and output and get the error. And with the help of the error, you change the parameters that govern the output, right? As for loss functions, we have MSE, which we'll be using thoroughly here because MSE is pretty intuitive to understand. The other cross loss functions are pretty similar, and they're really useful in their own ways. If you have time, please read them because they have some really brilliant reductions and really good mathematical sense behind them. Then this is the math behind the gradient descent, right? The first part, that is this, essentially means that you take the partial derivative of w with respect to y. Now, when I say partial derivative, please don't get scared. It's basically slope, right? If I just I'll go back to this particular example. I really like showing this off, but like I said, when you're at this point and you want to reach the minimum, right? So this is the error function. When you plot the error function, you get this. Let's just assume, right? Now we want the error to be minimum, and the error is minimum right here, and we are right here, and we want to reach here. We need to reach where the error is minimum. And how do we do that? Simply by following the slopes, right? The slope point towards the particular minimum. So a small example is if I keep going, following the slope, I will keep following, and keep going until it reaches the bottom, right? So this particularly means the slope, and once you find the slope, you travel in the direction of the slope, and this equation embodies that, right? So W minus the learning rate into the slope means you're moving to in the direction of the slope. Same thing goes for bias. Now there are two terms you must understand here. That is backpropagation. Now backpropagation is in simplicity this particular equation. That is the chain rule, right? For example, in case you want to find the derivative of w with respect to y, then you'd have to first find the derivative of w with respect to z because w first depends on z. and y and z depends on y. So there's order. So you go back the layers, hence the term back propagation. And I hope there's no doubts in that. Finally, we did a bit of how we use autograd, that is to find the particular gradients. Loss.backward find the gradients, and optimizer.steps updates it, right? The equations are here, so you can just correlate it. And this is something you must remember. It's a very important point. And optimizer.zero grad is used to zero the gradients. This might be a little confusing because you really don't know what do you mean by zero the gradients. But I explained in the last class. I'm just going to explain it again. Loss.backwards stores these particular gradients in some particular variable, and every time you call it, it just adds the new loss to that particular variable. It does not replace it, right? So it accumulates the gradients, which we don't want. We want the gradients to be fresh every time, right? So that's why we use zero grad to kind of reset that particular variable so we can get fresh gradients every time. So that's it for the review. If you have any doubts, now would be a great time to ask. I'm gonna keep an eye on the chat. So anybody any doubts, you can go ahead right now. Or if you have any suggestions whether you want me to go slowly or a little bit fast, anything. All right, I'll take the silence. Let's move on. Okay, so like we start this time, we're starting off with neural networks. They are inspired by how our brain functions, and the basic block is a neuron. A neuron is nothing much but a mathematical construct. So what a neuron does is it takes inputs. So x1, x2, x3 through x4 are inputs, and with each input there is a corresponding weight, right? That's w. And once we pass it through this particular block, we multiply them and add them. So x1 into w1 plus x2 into w2 plus x3 into w3 plus x4 into w4, and so on, right? And after that, we pass the whole thing to the activation function, like so. We have activation function here. So similarly, we just pass it through the activation function. Now, a neural network is made of several such neurons binded together. So you can see that there are a bunch of neurons, all of them are receiving inputs and all of them are giving outputs and so on. The first layer is always called the input layer, the last layer output layer, and whatever is in the between is known as the hidden layer. Now, another small thing to note is that for those of you new to neural networks, the number of neurons is not predetermined, nor there is an algorithm for it. What you need to do is find it through trial and error, and there's no sure short way of figuring out how many neurons will work the best. Same thing goes for learning rate. All right. So like I mentioned, a node will assign a number known as weight to each input. And once that's done, we just multiply and get the summation of it, right? Now, if that number is below threshold value, the node passes no data to the layer. This particular line actually refers to the bias. In essentiality, what a bias does is if you get a particular output and say you add a bias so that if that number passes a particular output, then only the neuron output will be positive. Say you have a neuron and you want to only get outputs that are, you want a positive output if the neuron gets a value of 5, and if the neuron does not get a value of 5, or if it gets value 5 less than 5, then you want a negative output, right? To basically do that, what you do is you add the bias as -5. So every time you get above 5, you get a positive number. So 6 minus 5 is 1, so on. If you get less than 5, you get a negative number, right? So that bias is basically used to figure out the threshold value. And this threshold value is again a parameter that the neural network itself learns. What is a good threshold value for this neuron, and so on. Like I mentioned before, they have three layers: input, hidden, and output layers. Now, all of the layers, number of layers, and number of nodes are hyperparameters. Hyperparameters being those parameters which we can optimize and that are not optimized by the model, right? Okay, there's a small note about different layers that we use to in neural networks. If you don't understand this, not a problem. There is convolution layers and recurrent layers. Convolution layers are usually used to work with image data, but this is something I would like to explore in a different workshop. It is actually one of my domain, my very interest, that is computer vision with deep learning. And recurrent neural layers used for majorly NLP. And Chakita will be doing a workshop on that later on. All right. So we know what a neural network is, how it looks like, and everything, right? Now we are interested in doing this in bias again, figured out by trial and error method. No, bias is not a hyperparameter. Chirag Anirudh, bias is not a hyperparameter, whereas bias is a parameter. That is the neural network itself figures it out. We don't figure it out by trial and error. So there are two types of things: parameters, normal parameters and hyperparameters. Hyperparameters are the one we have control over, like the number of layers, number of nodes, or the learning rate, and we can figure out what we need. And parameters like W and B are something that the neural network has to learn on its own. Now moving to this particular slide. So here is a general roadmap to how we do anything in PyTorch, especially building models. First thing is we get data. So this particular workshop will be doing the Mnist data, that is a 0 through 9 handwritten images, the thousands of them, and we have to classify them, right? Seems simple for us, but making a machine do this was something of a paramount success in the earlier days. A fun note to add, though, that neural networks and backpropagation was actually a very old idea. It originated in 1980s to through 1990s. The original papers date back to at that time. The reason they are very famous right now in this particular decade is because when they were originally invented, they were seemed to consume a lot of resources. That is, they needed a lot of computing power, which was simply not available. And coming to 2010, bam, we have a bunch of GPUs and CPUs which are available to everybody, and that's a really huge boost in AI because we had the computing resources that could drive these algorithms. Fine, we have neural networks now, right? Let's get to it. First thing is get data, divide to test and train. Now, this is a very important concept, test and train, and I would like to revisit it right now. The reason we need two data sets, test and train, is when you give something to train on. For example, if I train you to recognize pictures of apples, right? And I have three apples which I have in my fridge, and I get it to you and I show them all. And for like 10 days, I show it to you and I tell you, hey, this is an apple. In this, assume that you don't know what an apple is. Now you see the particular thing, and there's two things you can do. You can either understand what makes it an apple, or second thing is that you can just memorize how it looks like. So whenever you see what I showed you, you'll say it's an apple, right? The thing is, when I show you the three things and keep training you on that, you will assume that only those three things are apple, right? And you will kind of nitpick on the details. If my apple say has a brown spot in the middle, you will probably see it and say, okay, fine. So all apples must have a brown spot in the middle, right? It makes sense. If you have never seen an apple before and I show you three apples and I show you only these are apples, then it's very likely that you're gonna be very strict with your classification. You're gonna say, okay, only these three are apples, nothing else is apple. Anything that looks remotely different. Say I show you another apple, but this apple has a leaf on it or it's half eaten. You will not say it's an apple, right? Same thing goes for a model. When you train it on a set of data, it kind of learns on that data and it might give a good accuracy on that data, but that is not a true measure. A true measure is how well this model performs on different data. Like I've shown before, if we have a bunch of apples and we train the model on this images of apples and say the accuracy is 1, it can identify all of the apples. But that does not mean it identifies apples in general. It just means it identifies apples in our data set. Hence, we need a test data set, a different one that the model has not seen, to test, how well the model generalizes, right? The second step is to create a neural network. So here, what we do first is write a class for neural network, add the layers. Second thing, choose optimizer and loss function. Finally, define a forward function. A forward function simply does, uh, what it says forward propagation. It maps the input layers to the outputs. The third and final step is optimizing, right? That is training. We go through the data at each step and find gradient and update the parameters. Simple. And testing, we get the accuracy up. So this is the very simple part. What we do with yeah, what we do with this is the roadmap we're going to be following throughout. Next, we have data loaders. Now, data loaders are utility function PyTorch, right? Data loaders basically what they do is when you give them a particular number of data, they can perform a lot of stuff to it, and they can give it to us in a more comfortable manner in which we can process it. And I'll be showing that in the notebook later. But for now, let's just understand this, that when you have training data, say training data is an array of which contains both input and output of the data we're feeding in, and shuffle is to batch size 64. And train data loader creates an iterator. If you know Python, you know what an iterator is. You can iterate over it, and each time you iterate, it gives you back something, right? In this case, each time you iterate a data loader, what you get is a batch size. Say your batch is 64, you get 64 data elements at once, right? Which is really useful for us. So you will understand the importance of this later when you start coding. But data loaders are utility tools. You can do without data loaders, not a problem at all. But we use them because we would like to specify batch size, and they also shuffle the data, which is good because random data is always good when you're training. Like I mentioned before, loader is an iterable object, and each call returns a batch of the data containing input and output. Right now, before we go into yeah, before we go to the next slide, I'd like to just go ahead with this particular example of neural networks. So, like I've shown before, there's input, there's output, and hidden layers, and all these connections are governed by a weight. So, I told you that each input is governed by a particular weight, right? And to which it's multiplied and then added. So here the weight is zero point 0.4, here the weight is 0.42. Initially, they're randomly done. Now, let me just choose a different data. Bit of noise, bad size of. Okay, now this is a very simple neural network. It takes in two inputs, x and x2. X1 is this particular axis, x2 is this, and they both correlate to a point on this graph, right? And our aim is to tell whether it's an orange point or a blue point, right? So this is the training data. This is the training data. Now we have this bunch of points, and we pass all of this, and whenever it's here, we tell it's orange, here it's blue. So let's just train it. Learning rate, activation, declaration. Yep. Okay, so as the epochs go, we are done out 38 epochs, and the test loss decreased, the training loss decreased, and you can see that there's a line drawn here, right? That means the neural network is learning to separate the orange ones and the blue ones. Now, whenever you give a particular point on this side of the line, it will tell you, hey, it's an orange. This side of the line, it will tell you, hey, it's a blue, right? Now, that's a very simple thing. But if you have something complex like this, it still can learn, right? So as you see, as it keeps learning and the test loss and training loss decreases, this is just the graph of how the neural network perceives this. But I think now this much training is enough. But you can see clearly now that the neural network learned, right? It learned on its own through the functions that whatever comes in this region is blue, whatever comes in this region is orange, right? So that's exactly, I just want to show you that. Coming back to the problem in hand, we're done with data loaders, and we're going to be going through a review of classes. And there are two things that I would like to point out, that classes have, first thing, they have an init function. So this initialization function initializes all the important stuff in the class in the beginning. Now, if you remember inheritance from your Python classes, super function is used to make the child class inherit all the methods and properties from its parent, right? Now, for example, you're taking a parent class, and you're building a child class, and you want the child class to take all the properties and methods from parent, you simply run super and then the name of the parent class and then init, which I'll show you in the notebook later. So this is just something to remember. The classes have init, and super functions make the child class inherit all the methods and properties from its parents. When I mean methods and properties, I hope you know I mean variables and functions of a class. Also, the next thing is a little bit interesting. So I did mention that neural networks with PyTorch. PyTorch has extensive GPU support, and the reason this is very famous and it's kind of good is that you get to choose what you want to put to the GPU, right? So what do I mean by that? So PyTorch has two things, that's CUDA and CPU. When the device is CUDA, it means CPU, CPU means CPU. Okay, that's a something. Now, first we check if we have a functioning GPU with NVIDIA drivers. So I just have to mention that PyTorch extensively supports NVIDIA. Other drivers, I'm not sure. I've not tried. So if you do .cuda is available, it will tell you whether your GPU is there and it has the correct drivers installed and whether it's ready for use, right? Now the most important part, important thing that comes is you moving stuff to your GPU, right? So we have the test and train data. Now, like I said, GPUs are faster with some stuff. They are better at handling multiplications. The reason being that most games require geometric rendering, and geometric rendering is basically vector algebra, and vector algebra is basically matrices. So GPUs have architectures that are very well suited to matrix multiplication and handling of matrices, but they are not great at other stuff. They're not good at IO devices, or some they're not as fast as CPU in some basic arithmetic operations, but they are unparalleled in matrix multiplications and they're optimized for it, right? So we can move stuff. So we have the test and train data, which is generally in our RAM, right? So what we can do is we can move this test and train data into the GPU. I'm pretty sure you guys have GPUs with a particular amount of storage on them. So I have an NVIDIA 1650 Ti with 4 GB RAM in it. So I can move the test and train data into that, right? So the GPU will have faster access because it's closer to the GPU, and also that the some operations are optimized. Similarly, if we have the model also, we can move the entire model to GPU and do the training entirely on GPU, right? So these are some miscellaneous functions which you might need. So just take a note of them if you want to cross check whether your system has this particular GPU or something. You can use you can use device count to figure out how many GPUs you have and how many is recognizing, and this is just to troubleshoot, right? So just remember this. So if you want to be using, so here we have x.2 device, right? That basically means x is the data, test or train or the model, and two device to device just shift it there. And if the device is CUDA, it shifts to GPU. If the device is CPU, it shifts to CPU itself. So that's some basic points. Next thing is neural networks first steps. Okay, fine. So we're gonna start. This workshop is actually pretty short. We don't have much going on because first thing, we have covered neural networks, we have covered using GPU, and the rest of the part will be me coding a small neural network to show you how it works. And later we'll have a small Q&A session if you guys want to chat, that is. But yeah, this is a very simple session. Like I said, it's a gentle introduction to PyTorch, and we do not want to do anything complex. This is just getting starting. We have later we have more specific workshops on this, and even guided projects which we are planning. Getting back to this, so first thing what we need to do to make a neural network is to define a class, right? Now let's just get our hands dirty. So I hope you guys have your collab open. So I want you to go ahead and open a collab notebook. Artificial neural network. Do runtime, change runtime type, select GPU, and save. For those who have not used collab before, if you go to runtime and then change runtime, you can get to use a GPU which is provided by Google. though it won't last for long. And they keep pulling support after a while. Otherwise, first we do is import all the important stuff. Now, don't really worry if you keep forgetting what to import and you keep forgetting the model names. As you keep doing projects, this will most likely become muscle memory to you. First, import torch, import torch vision. Now, I'm just gonna outline and tell you exactly what this do. So, torch vision is a computer vision based module, right? Which helps in some computer vision tasks and also has data sets, image data sets inbuilt, which we will be using. I told you we're using Mnist, and Mnist dataset can be taken from Torch Vision. Next, we have import numpy as empty. Import matplotlib dot pyplot as pl. Yep. And done. Okay, so now the first step is get data. So let's do that. Now I told you we're getting data from the Torch Vision. So first we get a train data set. Get data set. Torch Vision dot datasets dot Mnist. How to use the GPU functionality. All right, so somebody asked how to use the GPU functionality. Uh, I'll get back to it. Just follow with me in the code. All right. So this will gather the Mnist dataset, which has already been put up in the Torch Vision module. Now there are a few arguments it needs, which is kind of trivial. If you look up the date, if you just look up documentation, say you go to Torch Vision datasets documentation. You can just end up seeing what exactly data sets are present. There are a lot of good data sets present, fake data, emnist, fashion mnist, even Cypher is there. And pretty much you will figure out what to do, and you'll also figure out what the uh, options do. I really encourage you to go through the docs. They may seem daunting, but trust me, they're really useful. You just have to get used to that huge amount of information, and you should know where exactly you would pick up your information from, right? So I just went here and I saw what data sets I need, and I figured out Mnist was right here. And after I saw Mnist, right, I just saw what the parameters are required. We need root, train, download, transform, target transform. And I just went through the parameters and I figured out what exactly I need to do, right? So if you're stuck anywhere, don't be shy. Go to the documentation. It's a great place. So train is equal to true. So this means you're telling them, hey, this is the train data, not the test data. Now comes an unusual part, which is not unusual really, but transform. So what transform does it applies a kind of function, right? For example, say Mnist has only color data, right? It has RGB data, all colorful, and we want it only to be in grayscale, right? So what we can do is maybe do a transforms dot to grayscale. There's a function that converts to grayscale, and say I have a function called grayscale. So what this does is transform applies grayscale to every data set element in the particular data set, right? So similarly, right now I don't want it to be grayscale, but I do want one thing, that is torch vision dot transforms dot tensor. Okay. Now what this function does is Now, Mnist data we get in forms of arrays, right? We get in forms NP, normally NumPy arrays, okay? And we want to convert this to tensor, right? So we transform, we add a parameter called transform, which transforms the entire data set into a tensor, right? So whenever you're working with image data or any data you want to convert, remember this particular line. Use a transfer when using Torch Vision. Finally, we have download is equal to true. Again, if you're mulling too much about what they do, just go over here and if true downloads the data and then puts in true and blah blah blah. All of them are here and they have a pretty good explanation. If anything, if you have any doubts, just put in the chat or ping me on Discord anytime. The document is a great place, really. Okay, cool. Let's get the train data set. Oh, all right. I think we got a data set. Let's just peek at it. Train D. Great. Number of data points 6000. It's a train data set, and the transform is 2 tensor. And to access the data, we just do dot data. Hey, here we go. We have all our pixel values and everything in this. Which is great. Let's look at the shape of this. So we have 60,000 data elements. 28 into 28. Great. So if those of you wondering what 2828 is, it's the size of the image. I mean, if you ever look up Mnist, basically get this, and each size of each image is 2828 pixel, and hence 2028. Great. Let's go on to the test data set now. Test T is equal to pretty much the same thing really. So let's just copy this code here. Paste. Only thing I would train is train is equal to false. And everything else is pretty much same. And let's download that and have a look at the shape of that too. Okay, good. So there are 10,000 data points. So usually trained data sets are larger than test data sets, which is good. Now we get into the main part. Right, now we create a neural network, right? Now how do we create a neural network? We make a neural network class, define a forward function, right? Class. Let's say an neural network. Now is where your Python skills come into handy. Use inheritance. Torch dot n dot module. Great. So torch.nn is the torch, that is the PyTorch unique neural network model. So there are two ways actually to create this. Okay, one, the most simplest way, which I have I'm not doing now, but is this. Okay, it's pretty similar to TensorFlow, but the reason we don't use it is it works for small models, but for bigger models we need more control. So we could have just done model is equal to torch dot nn dot sequential, and then add it on each layer as we want, nn dot linear. And whatever you add there, and nn dot value, and so on, right? We could have just done this way also, but the reason we're using a class is we also want additional functions. And further, neural network simple, we don't need much functions. When you're building other models, you'll need a class because there are a lot of other functions which you need to incorporate inside. So first thing is init, like I told you. And if you know object-oriented programming, you should know that it's always self, unless you have something else you want to put in there. Now, second thing, important thing, like I mentioned before, is this the super function. So super neural network self dot. Okay, now you must know what super does. So super takes in this particular class, the child class, and chuck. Okay, and what it does is it gets down the particular attributes and methods of that this torch.nn class into nn, right? So normally, this is not an alien syntax. So whenever you use super with any class, not just in PyTorch, use this, right? So first thing is the name of the class, then self and parameters if you have any. We don't have any, so it's just self, and then init. So initializing the parent class inside this class essentially. Okay. If you have any doubts, just go up and look up what super does. There are a bunch of tutorials on that. So now here we start building the model. Okay, so the first layer we're going to build is a flattened layer. The reason we're building a flattened layer is that we have a 28 into 28 matrix, right? It's a 2D matrix, if you remember. But we do not want it to be a 2D matrix. We want it to be something like here. So there are only three. There's no 2D matrix input. There's a line of input. So we flatten the 2D matrix into a 1D line, if that's understood. Go ahead. We haven't self.init. Okay, next. Self dot. Okay, so once we're flattened, let's add a particular one. So this particular code is taken directly from the documentation itself. If you look up the documentation somewhere, you should find it. Sequential. Here it is. So we are using a pretty much similar model. So let's just say we just say linear hidden layers is equal to torch dot rn dot sequential. First we add a linear layer. I want to, or I don't know, we go for 5 minutes. Okay, so the first line, nn dot linear. So what nn dot linear does is it creates a small neural network with 28 into 28 is around 784. Yeah, around 784. So what it does is it creates a neural network with 784 nodes, right? And the output has 512 nodes. So it takes in around 728 inputs and it gives out 512, right? So the input number will be 728 and the output is going to be 512. That is, they're going to be 512 in this layer, they're going to be 728 in this layer. So first thing, nn dot linear, this is the input nodes, output nodes. Nice, that is done. Now nn dot relu. Now I'm not sure how many of you know what relu is or what activation functions are, but that's something I want to address. So activation functions basically in the most essential sense add in non-linearity to an function, right? Coming back to the example we had before of a neural network, this function xw plus b is a linear function. If you plot it, it'll be a straight line, right? But we have seen here that not always that a straight line find the gap or distinguish. In this case, sure, a straight line a straight line can distinguish between them, right? But if you go in this case, this is not a straight line. This is pretty much a curve, right? So the equation cannot depict, and if you do the equation which we used here all as usual, we can in no way recreate this particular curve, right? So what activation function does is it introduces non-linearity. It makes this particular linear function be able to depict non-linear functions like curves and so on, right? So ReLU is one of the activation functions we use. You should definitely read up more on it if you do not know what it's used for. So nn.relu. I think I might have done an issue there. ReLU is invalid syntax and you, yep. After that, we have another linear layer. So linear layer, the input of the linear layer should be output of the previous layer. So 512, say we give 512 only as usual. We're just going to follow the docs for this one. And nn dot ReLU again. Activation function after every time. Let's not forget that. And nn dot linear again. The input should be the output of the previous one. That's 512. And finally, let's make this output layer. So output will be 10 because there are 10 numbers and we have to identify them. Right? Finally, activation function as usual. Right, so we are done with the hidden layers, flattened layers. So that's done. Right, now the next thing we need to do is define a forward function, right? So define forward. It takes self and x as input. X is the input which we're giving. A forward should just put it through neuron and get it out, right? So first, what it does is it flattens it. So self dot flatten x. So x is flattened now, and the output to the self dot linear hidden layers of x. And we return out. Awesome. So what we do is we have a forward function. It takes in an input, and like I said, we have to write the input. What happens to the input? So first thing, what happens to the input? That is flattened, right? We wrote a flatten function here, so we send it there. Next thing is it has to go through all of this, so we send it through this, right? And we get the output, and then we return the output. So forward does forward propagation, and yeah, we're golden. Now let's make a model. Model is equal to nn. Great. Yeah, done. Now we have a model which is ready. Now I'll be going into the GPU part. We have to move it into the GPU, right? So first thing, device. Now, like I mentioned before, we have to check if CUDA is available, and only if it's available, we can put the device as CUDA. Otherwise, default will go to CPU. Okay, so let's do that. So first thing, let's make a variable is CUDA, or let's just put a simple if statement. If torch dot CUDA is CUDA dot is available, then device is equal to torch dot device CUDA. else is just equal to CPU. Okay, so right, so since GPU is available, the device became a particular GPU device. Now I told you we have to move the model to GPU. How do we do that? Like I mentioned, x.to device, right? So model dot to device. Oh, sorry, just to. I made an error in that. It's just model dot to. Yeah, it takes some time to move the entire thing to GPU, but yeah, that should be done. All right, so it's done. The entire model is moved to GPU, which is great. Now we can start off with the rest of the part. That is nice. So next thing is for optimization, right? So let's go back here. And first is loss, as if you remember from the last class, loss function. Now the rest of the frame is pretty much same. There's nothing much of a difference. Now since this is a classification problem, we're going to take cross entropy. I told you that there are many types of loss suited for different things, and for classification tasks, cross entropy is much suited. So I'm going to use that. And now optimizer. All of the cross entropy, though, we had actually covered this in the previous sessions, which we held like 3 months back when we had deep learning sessions. We have covered all the loss functions and all the optimizer functions. If you guys have any of you attended that. Now model.atom or SGD, whatever you feel like. I usually use atom, but since we learned using SGD, let's use that. And running rate is equal to 0.0. Let's just go for that. Okay, cool. Now let's next thing is the data loaders. So like I've said, we're going to use the data loaders to get the training data which we got, test data which we got, into a data loader object, right? So let's do that now. So let's make the batch size let's say some 16 or something. And now train loader is equal to dot utils dot loader. Now the dataset is train dataset, and batch size is batch size. And let's shuffle the data. Great. Now let's go for the trained tutorial loader, test loader, and this would be test D. The rest will be pretty similar. And let's go. Oh, forgot. All right. So like I've shown here, the data loader is in torch.utils.data. I didn't import it. I directly just went to torch.util.data or data loader. So we have a data loaders now. So just to show you what the data loaders do, let's just take a temporary data loader. Pretty much the same thing. Let's see the batch size as 1. And no, I told you it's iterable, right? So for x comma y, x is the input. So usually in iterable it gives you input and output. So input dot output in tmp dot t int. Right, so every time it returns 1 because batch size is 1, but in case I had batch size as say 5, and after that I just print for sanity check. Yeah, so you can see that each time it gives a batch size of 5, right? And the torch size is always let it go. So it has the image that we want 2020 and 5 of those because batch size is 5, and the output is just 1, so it's a 5-dimensional, I mean 1-dimensional array containing 5 elements, and each element is, say, whether it's 1 or 0 or 2, whatever the number is, right? Like in general, the notation goes something like this: that you have the image that's 1 into 28 into 28 size, and the output is just like one number. If it's 9, it's 9. If it's 8, it's 8, and so on. Otherwise, now we have the most important part, that's optimizing. So let's go over that. First thing is epochs. So EP is equal to 10. I'll go for 10 epochs for now. X. I wanna, keep the train losses. Do I want to keep it or not? Yes, fine. Let's do that. Let's skip that for now. I want to confuse you guys. So let's go. So like we told before, it's simple for epoch in range epochs. So for each epoch, we do a pretty simple thing. For inputs, comma outputs in loader. Now, next important thing is move them to GPU, right? Now, like I said, we also move the test and train data, but the thing is we don't need to move the entire data beforehand because we'll just be moving the data we're using, right? So for this particular point, we're using just a batch of 16. So we'll be moving only them. So we can just just equal to dot to device. Similarly, out is equal to out dot to device. Right, done. Anyway, let's go. So we're done with the outputs. Now let's go to the next part, that is reshaping. Input is equal to this is just a simple thing to make the data more. Because we're passing data, we need it to be in this particular format. So this is utility function view. It just resizes the data shape. Now next part is what we all know as usual, 0 grad. So optimizer we chose, yep, optimizer dot 0 grad. Next is for propagation. So output required output should be equal to model and inputs in them. After that, we have loss, which again, using the loss function, which we've done before. Pretty simple. We just take the outputs that we got and the output which we have. Right, done. Now, next, what we do is pretty simple. Once we got the define the gradients, find the gradients is also pretty simple. Loss dot backward, if you remember. Now the gradients are computed and stored. Now we do is update params. How do we do that? Optimizer dot step. And to be fair, this is all. There's nothing else to do here. Say I just end up printing the epoch number and loss dot item here each time. So we just figure out what's going on. Other than that, let's just go for training. What happened here? Registered okay, it's not implemented error. Oh, name it as labels or something. Okay, hold up. I made a mistake here. Input and outputs. So let's just convert them to inputs. Targets equal to inputs. Train loader done. Inputs and outputs is inputs. Convert to targets. Output is out. Convert to targets. After that, inputs is equal to reshape and zero the grad, and then output should be equal to model into inputs. Loss is equal to loss function into outputs, and the targets of the backward loss dot step. Incredibly weird. What does the dataset contain? What is the BIOS image of handwritten names? Those of you here, did you figure out, did I miss some variable here somewhere or anything? Meanwhile, let me just search for that. Are you getting the same error as me, or is it just I have to restart my notebook or something? Can you just confirm on the chat if you're coding along with me? Are you all getting the same error if somebody's coding along? Oh, okay, never mind, I got it. The issue was that I had in a forward class and I forgot to use it. Oh, great. So model dot forward. Where that forward inputs? Model. Set for flatten X. Then after flattening it, is anybody else coding along? I just want to know if they have the same errors. Are you getting same error? Okay, cool. I might have missed something up here. Um, just give me a minute. Let me just go to the code. We have a neural network. We have a flattened layer. We have a stack which has exactly the number of required target error. It's around 10 layers. Returns this. Made a model. Is the optimizer. Yeah, model parameters. Then we have training loop. We move these to device. What am I missing? It worked a while back when I was just trying this out. We have the tensor. Input outputs are working properly. We need our should be equal to model, whatever we have, and the inputs which we have in the same manner. This error usually ends up coming apparently when classes mess up. Let's just check that. We have a ReLU function. We have torch. Supermodel is also initialized with the neural network, and they're initialized. Let me just try using the one they're given in the documentation directly. Initialize this. Model and then move it to device. Network function batch. Then the optimizer. Okay, great, it works now. Okay, those of who are facing the same error, not entirely sure why it's that was the case. My code is pretty much similar to that one. Initialize the function super of that neural network, and then flatten torch a large number of numbers. What is that? Okay, that ended up showing in multiple comments, but yeah, just copy this instead of the original class. I'm not sure what the error is. They're pretty much same. I don't see any issues. Maybe NN is an identifier, capital NN. I'm not in. Yeah, it might be that case. Oh my god, that'd be very stupid. But yeah, just copy the same thing. It's pretty much same. If you can, just try your class, change your class name, and tell me if it works for you guys. It was working for me. I'm getting a large number. Yeah, that's exactly what it needs. So maybe there's one thing you need to do though. Let me just stop this once. And yeah, the loss dot backwards, optimizer dot step, and your print function should be here. So each time you go into there, let's make a variable called loss, put it to 0, put it to 0, and then right here, once you get your loss, say train loss at each epoch, and once you get your loss, just add train loss plus is equal to loss, right? And at the final step, print epoch number and loss dot item dot train loss divided by 50. Great. Now it starts training, and you'll see the loss every epoch. Before I just put it in the wrong for loop, so you keep getting it every time, which is fine. See in the 10th for loop now the loss is zero point 0.6, then it's 0.5, and it keeps going down. This should be epoch, by the way, not EP and Fisher. Yeah, that is essentially right. Almost what you got as the output, Muhammad Ayan. And no, it was not the intention. I think it was mostly because NN, capital NN, is reserved for in torch.nn. That's why this small class was not superseding, which now makes very much sense. I should have changed the name, but that's the same. I guess you can just try changing the class name and try. It should work, right? Other than that, this particular thing, just change the class name neural network and then do pretty much the same thing. There's nothing different to do. All your, and to remove this thing, just import from torch nn, right? So there's a small hitch that I messed up this naming condition. Other than that, it's pretty much same. There's nothing else to worry about. You got the loss function optimizer, you have the batch, the train loaders, and while you're optimizing, let me just explain this code once for sanity check. So you go through each epoch and you have a train loss. This is just to keep a note of your losses. Okay, so you go through each of them in for input, output, and train load. It'll give you a batch of 16, right? So it'll give you 16 data elements at once, right? So input and target are both 16 data elements once. Now you zero the gradients, you pass in the inputs, you get the outputs. Now you find the loss using the loss function. Now this is just basically us taking the loss and adding it here so we can print at the end. Finally, find the gradients. Finally, update the parameters, right? And then for each epoch, just print the epoch number and the train loss divided by 16 because we keep adding, but we need the average and batch size is 16. So average should be just divided by 16. So as you can see here, initially the loss was high. It was 0.16. And each time we keep training, the error kept decreasing. Now it's 0.03, which is very good. Error is very less, right? Now, what is the use for this? The use for this loss values is just for us to figure out whether our neural network is working better, right? If the loss is less, that means the neural network is working better. That is, error is less. Did you understand that? So for now we are done. So basically, this is how we optimize a particular neural network, and this is the general skeletal code you can follow for on any network. If you're doing RNN or you're doing a CNN, it'll be pretty much similar, right? You get the input output from the train loader, and then you put them to the device, input and output targets, and you end up doing this, right? So you have any questions right now? Anything? All right, I'll take that for a no. I'm gonna stop presenting for now. Um, all right, so that was basically the workshop I wanted to go through. There was a hitch in the core base because I stupidly named our model NN, but the rest of it is pretty much simple. We got the data, we got test and train data, we created a neural network with classes with the forward function, and then we moved everything to the GPU, and then we did the optimization loop, which I wanted to show you about. So essentially, in PyTorch, everything is pretty much similar. And while I have you here, let me just go through something. Go to PyTorch. So I want you guys, whoever I left here right now, to just go through the docs for PyTorch. Their official website has awesome tutorials. You really, if you can understand it, you will understand it way better there itself. And you have some very interesting stuff here. If you think this is too much, then just go head over to the tutorials, and you will find some easy stuff to start off with. Which you can do here: saving, loading model. So, like I told you before, say we're going for torch vision, computer vision. Let's say this. So I just want to tell you that normally when you create the data set, it goes around like this, and then we create the model using classes and then functions. Where is that thing gone now? Putting everything together, infra forward, device. Yeah, and like I told you, the model, that is the training function, is pretty much same everywhere. Okay. Here also we keep going to the training function. We get the data loaders here. Data loaders are used almost everywhere. And after we get the data loader, what we do is we train the image, right? And like I said, we also keep using the GPU more because we keep moving them to GPUs, and then we keep trying to schedule them. So here also you see the training, right? For a epoch and range number of epochs, train one epoch, and then scheduler dot step. So this is optimizer, it steps, and then we evaluate using custom function. So all of them follow a very same approach. So if you understood the fundamentals of this, you should be good to go with the rest. So that's it from my side. If you have any doubts, please put them in. Other than that, those who have no doubts, thank you for attending session and staying till now. You may leave. All right, guys. Thank you very much. I'm gonna leave now. Bye bye.